Our solutions for perfect problem 6 for Math 251. We're given this function, which it might help to rewrite as x to the 1/3 power times x plus 6 to the 2/3 power. Then asked a bunch of stuff. First, find the critical values. To find the critical values, you need to know that critical values come in two different types. When the first derivative equals 0, and the second type is when the first derivative is undefined. So either way, we need to know what the first derivative is. Let's figure it out. First derivative, well, let's see, it looks like I got a product of two things here. So I could use the product rule. The product rule tells me that the derivative of the product of f times g is f prime, which would be 1/3 x to the negative 2/3, times g, which is x plus 6 to the 2/3 power, plus g prime, which would be 2/3 times x plus 6 raised up to the negative 1/3 power, times the derivative of x plus 6, which just happens to be 1, times f, x to the 1/3 power. Get this mess right here. This is f prime g plus g prime f. This is your derivative. How the hell are you going to figure out when that thing's 0 or when that thing's undefined? Well, there's a little hint here. It says factor 1/3 x to the negative 2/3 times x plus 6 to the negative 1/3 from your derivative. Okay. So I got two terms. Here's one of the terms. Here's the second term. And from each of those terms, I'm going to attempt to factor out 1/3 x to the negative 2/3 times x plus 6 to the negative 1/3. If you do that, you'll have stuff left behind, right? I got two terms. So I'll have stuff on this side and stuff on this side. What will I have behind? Well, let's look at this first term right here. The 1/3 is gone. I pulled that out. The x to the negative 2/3 is gone. I pulled that out also. I used to have x plus 6 to the 2/3 power, but I factored out x plus 6 to the negative 1/3 power. So I used to have 2/3 of these things. I took away negative 1/3 of these things. So what's left is 2/3 minus negative 1/3 of these things. In other words, x plus 6 to the 3/3 power, which is just to the first power, which is just x plus 6. Sure, x plus 6 to the 1 if you want. Although that kind of looks like prime, so I'm going to not write that. X plus 6. That's all I have left from this term when I factor out all this stuff. What about this term? Well, I had a 2/3 and I took away a 1/3, so I still have a 2 left. I had x plus 6 to the negative 1/3 and I took away x plus 6 to the negative 1/3, so that's completely gone. I had x to the negative 2/3 and I had x to the 1/3 and I took away x to the negative 2/3. So I had 1/3 of these things and I took away negative 2/3 of them. You had 1/3, you subtract negative 2/3, you have 3/3. In other words, you have one of these things. What I'm getting at is our derivative simplifies pretty nicely if you factor out all that junk. It's 1/3 x to the negative 2/3 times x plus 6 to the negative 1/3 times, well, let's see, x plus 6 plus 2x. That looks like 3x plus 6. If you want, this is just a bunch of stuff multiplied together. You can multiply it in any order. I can take the 1/3 and multiply it into the 3x plus 6 and get x to the negative 2/3 times x plus 6 to the negative 1/3 times 1/3 times 3x is just x. 1/3 times 6 is 2, so times x plus 2. This is the derivative, as is this, as is this, as is this. I like this form the best. You may or may not. That algebra might have been a little bit much for you, so you might not like this form so much. But whatever. I mean, whatever you got. Any of these, they're all equal. You can use any of them. I just think this will be the easiest to deal with. This times this times this. And when I say deal with, I mean, we still haven't figured out anything. This is just the derivative. We want to find critical values. So critical values happen when f prime of x equals 0 or when f prime of x is undefined. F prime of x equals 0. I got x to the negative 2/3, which I can write as 1 over the cubed root of x squared. That's x to the negative 2/3. I'll multiply that by x plus 6 to the 1/3, which I can write as 1 divided by the cubed root of x plus 6. I'm going to multiply that by x plus 2. I want to know, when does this times this times this equal 0? Well, product of things equals 0 when any of the things in the product are 0. What I'm saying is if this thing right here is 0, 0 times anything is 0. So if this is 0, or this is 0, or this is 0, I get a critical value of this type where f prime of x equals 0. This is never 0. How do you know this is never 0? Because there's nothing you can divide 1 by to get 0. What about 1 divided by 0? That's not 0, that's undefined. Oh yeah. What about 1 divided by 1? No, that's 1, that's not 0. Damn. What about, yeah, I guess there's nothing. There's nothing you can divide 1 by to make this term equal to 0. This term will never be equal to 0. By that same logic, this term right here will never be equal to 0. There's nothing that I can divide this 1 by to get 0. So the only possible way this times this times this can be equal to 0 is if this thing right here is 0. When is this thing right here? So maybe like, I mean, I guess you could write it this equals 0, this equals 0, this equals 0, and then say there's no solutions to this one, no solutions to this one, and solve this one. But for the sake of saving space, I'm just going to say x equals -2. Where did that come from? Well, if this thing is 0, the whole thing's 0. When is this thing 0? X plus 2 equals 0. Subtract 2 from both sides, you get x equals -2. What I just found is a critical value. One of them. It turns out there's 3 of them. What are the other ones? Well, they're not of this type. They're of this type over here. F prime of x undefined. F prime of x is undefined when you divide by, well, you can't divide by 0. You can't take the square root of a negative number. You can't take the log of something that's not positive. Those rules. No logs going on here that I have to worry about. No square roots. Yeah, there's cubed roots, but that's okay. No square roots going on in here that I'll have to worry about. So really all I have to do is make sure I don't divide by 0. What values of x will make you divide by 0? Well, I'll divide by 0 right here if x cubed, so I don't know, I guess I could copy this exact same thing right here, figure out when it's undefined. But it's undefined if I divide by 0 on this first factor. What will make you divide by 0? If x equals 0, because 0 squared is 0, the cubed root of 0 is 0, and 1 divided by 0 is undefined. So if x equals 0, this first term is undefined, so the whole thing is undefined, so the derivative is undefined. Well, at the second term, can this ever be undefined? Well, kind of the same logic. If x is equal to -6, -6 plus 6 is 0, the cubed root of 0 is 0, 1 divided by 0 is undefined. This third term, no, that's never undefined. X plus 2, plug in anything you want for x, and you can add 2 to it. So what I get is there's 3 critical values. 1 of this kind of first type, and 2 of this second type. Those are my critical values. All that to finish part 1. Fortunately, I think 2 and 3 will go a little bit quicker once we have those answers. 2 says, classify one of your critical values as a local max, local min, or neither, using the second derivative test. Hint, this is the second derivative right here. Coming up with this second derivative is a pain. I don't even think I'm going to do it. You can do it if you want. I mean, okay, I'm not going to do it, but maybe I'll write easiest way. Take the derivative of this guy. So a product of 3 things, you're using a product rule inside of a product rule, and you get some huge mess, right? Because multiplying together 3 different factors, oh, that's going to suck. But you can do it. Take the derivative of this guy right here, and you're going to get something that looks nothing like this. But it's going to be equivalent to this. How do you show that this is equal to this? Take the derivative of this, then factor out what you know the answer to be. -8x to the -5/3 times x plus 6 to the -4/3. Wait, factor that out. What are you talking about? All right, if you take the derivative of a product of a bunch of things, you're going to get the sum of a bunch of things, something plus something plus something, because we'll be using the product rule. Take this thing out of each of those terms. It'd be kind of weird to factor these things out with negative exponents. It'll be just like we did over here where you were factoring out negative exponents. Do that. Take that out. And after you take that out, you'll have a bunch of stuff left from each of those terms. But what you'll see is that stuff left from each of those terms, you combine it all and you just get the number 1. How do I know you get the number 1? Because it has to be. The only thing you can multiply this by to get the final answer is the number 1. So take the derivative of this guy, factor out this mess, and then just show that what's left inside is just the number 1. Then you're done. I'm not going to do it. Sounds like a lot of work. I'm just going to assume that I'm going to use this hint right here. Anyways, part 2 says, use the second derivative test. And it's kind of a tricky question. It says, use the second derivative test to classify one of your critical values. That was kind of mean. Trick question. It's a trick. Can only... What I'm going to write up here, I can't write and talk at the same time, which is unfortunate for making these videos. You can only use the second derivative test on critical values of this type. Those critical values where the first derivative is undefined, you can't use the second derivative test on them. Can only use second derivative test on the f prime of x equals 0 type. So really, it's a classify one of them, making it sound like you got a choice. You don't have a choice. You can only classify this guy right here. How do you do the second derivative test? You take this critical value and you plug it into the second derivative. You figure out f double prime of -2. And really, you don't even care what this is equal to. You just care whether this is a negative number or a positive number. So let's see what this is. It's -8 divided by -2 to the 5/3 power. Instead of writing x to the -5/3 power, I put x to the 5/3 down in the denominator. It'll make it easier for me to figure out if this thing is negative or positive, which is what you need to do with the second derivative test. And then I want to multiply that by 1 divided by -2 plus 6 to the 4/3 power. That's just this guy right here, except instead of raising it to the -4/3, I do 1 over it to the 4/3, and I change the x to -2. I just got to figure out if this thing right here is negative or positive. This thing right here, it's negative. 100% it's negative. A negative number raised up to the 5th power is still negative, and the cubed root of a negative number is still negative. So right here is a negative. So right here is a negative. So I got a negative number divided by a negative number times 1 is a positive number divided by, what's this mess down here? Is this negative or positive? Turns out it's positive. Because this 4 right here is an even number, it's automatically positive. If you raise something to an even power, it makes it positive. And you take a cubed root of it, it's still positive. Another reason it's true is because -2 plus 6 is a positive number, and a positive number raised up to any exponent, negative or positive, is not going to be negative. It's going to be a positive number. So what I get is, this is a negative divided by a negative times a positive divided by a positive, which is a positive number, and what that tells me kind of counterintuitive, that -2 is a local minimum. If the second derivative is positive, that means you have a local minimum. Why is that true? If the second derivative is positive, the shape of your graph is concave up. In other words, it looks like this. If it has this shape and the first derivative is 0, we're talking about that point right there. Note that this point right here is a local minimum. Second derivative is positive means it has this concave up shape. It does not have this concave down shape. That's number 2. Number 3, guess I need a new color, huh? That's how you know a problem's bad, when you get into the purple parts. Number 3 says classify the remaining critical values using the first derivative test. The first derivative test, it's not that fun. So 0 and -6. The way you use the first derivative test is you make a number line. You put all of your critical values on the number line. So here's 0, here's negative, maybe 0 is way over here. Here's 0, here's -2, and here's -6. Note that those 3 critical values divide my number line up into 4 different regions. Got a region over here, region here, region here, and region here. The idea with the first derivative test is I know that at each of these points, the first derivative is either 0 or undefined. If I just knew the sign of the derivative a little bit to the left or a little bit to the right of those points, I could figure out if the function maybe, let's say that, okay, pretend this is positive and this is negative. What that means is my function used to be increasing, now it's decreasing. What that means is that at this point right here, I was at a local maximum. That's the idea of the first derivative test. So let's do it. So the first derivative test, I pick any number. So let's test region 1. Pick any number in region 1. It doesn't matter what number it is. So what I'm saying is any number less than -6. -6.1 if you want, or -5,000 if you want. It makes no difference. Any number less than -6. Test region 1. I'm going to arbitrarily pick, I don't know, x equals -10. I like 10s. They're good round numbers. X equals -10. And I'm going to figure out f prime of -10, kind of. I'm not really going to figure out f prime -10. I'm going to figure out if f prime of -10 is negative or positive. Let's look at this thing right here. -10 to the -2/3 power. I claim that's a positive number. Why is that true? Because it's the same as 1 over -10 to the +2/3 power. And -10 to the 2/3 power, this 2 right here is going to square the -10. It's going to make it positive 100. Then I'll take the cubed root of 100, which will be some mess, but I don't care what it is. The cubed root of a positive number is positive. Because this 2 is an even number, no matter what I plug in, -10, -5, -1, +5, whatever the hell I end up plugging in, first term is always going to be positive. What about my second term? X plus 6, so -10 plus 6 is -4. -4 to the -1/3 power. I got to figure out if that's negative or positive. Maybe I'll write it this way. I claim it's negative. Let's justify that. -4 to the -1/3 power is the same as 1 over -4 to the 1/3 power. In other words, it's the cubed root of -4 is down in the denominator. The cubed root of -4 is a negative number. 1 divided by a negative number is a negative number. The second term is negative. Then finally, this third term, -10 plus 2, is certainly negative. That's one I can do. -10 plus 2 is -8. Doesn't matter what it is, just the fact is it's negative. Positive times a negative is equal to a positive number. So what that means is the first derivative is positive everywhere in region 1. Not just at -10, but everywhere in region 1, because the only places where my first derivative can change sign are at one of these critical values here. Now let's test region 2. I'm going to arbitrarily pick any number in region 2. I don't know, -3. And figure out f prime of -3. See, the first term, it's always going to be positive because of this 2 right here. It's 1/3 times -3 to the -2/3 power, which is the same as 1 divided by -3 to the +2/3 power. The 2 in that 2/3 power means square. Square anything, it becomes positive. This first term is positive, and it's going to continue to be positive for region 3 and region 4. What about the next group? -3 plus 6 is a positive number. A positive number to any exponent is going to be positive. -3 plus 6 is positive 3. 3 to any power is positive. What about -3 plus 2? -3 plus 2 is -1. That's a negative number. What I get is a positive times a negative, which is negative. It means that my sign in region 2 of the first derivative will always be negative. 2 more of these. Maybe I'll go a little quicker. In region 3, pick any number you want. I want to pick -1. F prime of -1 is going to be positive times, let's see, this second guy, -1 plus 6. It's a positive number. Raised up to the -1/3 power, still positive. -1 plus 2, that's a positive number. You get a positive times a positive times a positive, which is a positive. Region 3, always positive. Region 4, it's not going to print very well, so I'll do it over here. I pick -1 for this guy. Any number you want greater than 0, I don't know. How about 1? F prime of 1, is it positive or negative? Well, this first thing, +1 to the -2/3 power, a positive number raised up to any exponent is positive. This second thing, 1 plus 6 to the -1/3 power. 1 plus 6 is 7. 7 is positive. A positive number raised up to any exponent is positive. What about this third one? 1 plus 2. 1 plus 2 is 3. 3 is a positive number. Positive times a positive times a positive is positive. Turns out that in region 4, first derivative is positive as well. A little bit strange. So what does that tell you? So let's see, we were testing critical values. What have we already done? We already tested the one at -2. We already tested this guy using the second derivative test. We concluded that it was a local minimum. Note that this confirms that answer. Negative means my function's going down. It used to be going down, now it's going up. In between there, it must have been at a minimum. -6 and 0 were the other two I wanted to figure out. At -6, it used to be going up, now it's going down. Sounds like a local max to me. What about 0? It used to be going up, now it's going up again. That's not a maximum or a minimum. X equals 0 is neither. Because I put an exclamation point there, I guess I should put them there too. We'll call that good. That's the end of this kind of long video, but hopefully by making it long I was able to illustrate lots of concepts and make this make some sense to you. So I will put a box around this and then end things here.